The yield equation is a fundamental baseline theory in crop science. I mean, if this yield equation is not true, then, all of crop physiology is also not true. Everything we know about it, we'd have to throw out and start from scratch. So if you think, if you're looking at this and figure out something wrong with it, just let me know as soon as possible. So the yield equation, don't be scared by the math here. I'll go through every term in the equation. So first we have y, which is yield, equals. We have the squiggly line. That squiggly line is an integral, but again, that's some calculus stuff we don't need to worry about here. What we're saying is we're taking the sum from t equals p, so from planting, to t equals h, harvest. So we're only looking between planting and harvest. And then we have PAR, which is total photosynthetically active radiation. Okay, Barry introduced this concept in previous lectures. So we're looking at all the solar radiation, or rather all the photosynthetically active radiation hitting a farm field, right? This is measured in terajoules per hectare. But we only care, as crop scientists, about the proportion or fraction of that PAR that's intercepted by the crop canopy, right? If it's just hitting the bare soil, it's not going to contribute to yield. So we use this term A, or alpha, which is getting us the fraction, a number between 0 and 100 of the PAR being intercepted by that crop canopy. Okay, that's being absorbed by the crop, and hence can be used for photosynthesis. So we take that PAR that's absorbed by the crop, all of it from planting to harvest, and we multiply it by the crop's radiation use efficiency, which again, a concept Barry introduced to you earlier in the course. Okay, so radiation use efficiency, it's expressed in terms of tons of biomass per terajoule of radiation absorbed. Okay, so that's giving us essentially, when we multiply PAR by that alpha multiplied by RUE, we're getting total crop biomass produced from planting to harvest. Most farmers only care about, or primarily care about, the part of crop biomass that they harvest and that has economic value. That's usually the grain. Okay, sometimes it's the straw, but most of the time it's the grain for temperate crops. So we multiply that total crop biomass by the harvest index. Okay, and that's a percentage, again, a fraction from 0 to 100%. That is the proportion of crop biomass that is allocated to the grain. So that is the yield equation. I'm never going to make you, for this class, fill in, solve the yield equation, fill in the terms with a bunch of numbers and figure out what yield is. That's not really the point of introducing it to you. The power of the yield equation is that any management practice that a farmer does, which increases yield, crop yield, is going to do so through one of those three parts of the yield equation. Okay, it's either going to increase the fraction of intercepted photosynthetically active radiation, it's going to increase that crop's radiation use efficiency, or it's going to increase that crop's harvest index. It's going to do at least one of those three things. So let's ask the question, how does weed control increase crop yields, or why are herbicides effective at increasing crop yields? It's the same question, or the flip side of asking, how do weeds reduce crop yields? And to answer this question, we can indeed use the yield equation. So the graph on the left is from a paper published by Dr. Clarence Swanton, recently retired professor from the University of Guelph. This is research he did at the Elora Research Station, where he essentially asked, and I think answered this question: how does weed pressure reduce corn yields? So what he did was he grew corn in weed-free plots, kept weed-free by either herbicide or tillage, and in weedy plots where weeds were not controlled. And then he took these corn plants and he measured leaf area at each leaf position. So the lower leaf positions would be closer to the ground. The upper leaf positions would be, the tallest at the uppermost leaves. And he measured leaf area, centimeters squared. And what he found was that corn plants in the weedy plots had much smaller leaf area than corn grown in the weed-free plots. So if we relate this back to that yield equation, because like I said, almost every management practice's impact on yield can be related back to the yield equation. Well, this seems clearly an effect that flows through that alpha, the proportion of incident photosynthetically active radiation that is absorbed by the crop. Quite simply, if a field is weedy, then that fraction of intercepted radiation will go down, and if that farm field is kept weed free, then the fraction of intercepted radiation will go up. So why do weeds reduce corn leaf area? Without going too much into the details, what happens is that when those young corn plants, corn seedlings, sense weeds nearby, and they sense it through changes in the red to far red ratio of light, what those plants do is they say, hey, I'm going to go really, really tall as fast as possible so I can get taller than these weeds that I'm competing with. And I'm not going to invest so much in having a very large leaf area. All right, so corn plants in weedy fields, they decide to grow taller quicker and sacrifice leaf area to do so. Nitrogen and water stress are both fairly common in temperate cropping systems, right? So there's often seasonal periods of water deficit, so there's not enough water available to support crop growth, and that can impact yield. Keep in mind the difference between crop growth and yield. Crop growth is total biomass accumulation of that crop, be that in the stem, in the roots, in the leaves, whereas yield is biomass accumulation, specifically in the grain organ, the part that is harvested because it has economic value. So nitrogen and water stress often reduce yields. This is a study that shows why or how nitrogen and water stress reduce yields. This is a study done in corn in New Zealand, actually. So this graph you see on the x-axis, nitrogen fertilizer rate, going from 0, where there would most certainly be nitrogen stress, all the way up to 400 kilograms of nitrogen per hectare, and there would certainly be no nitrogen stress there. They did this study in a dry land, so with no irrigation, and then in an irrigated field. And so certainly there would have been water limitation in the dry land field and none in the irrigated field. And on the y-axis of this graph, we can see radiation use efficiency. And it's expressed here as grams of dry matter per megajoule of radiation absorbed. And that varies here from 0.6 grams per megajoule to looks like 1.3 or 1.4 grams per megajoule. And what we see quite clearly in this graph is that as nitrogen fertilizer rate increases, from 0 to, say, 300 kilograms of N per hectare, as we relieve nitrogen stress, indeed, radiation use efficiency goes up. And so when we think about how does nitrogen fertilizer increase grain yield, at least in corn, it does so by improving radiation use efficiency. Then we can also just look at the effect of irrigated versus dry land. Okay, and again, the effect of water stress here is apparent in its impact on radiation use efficiency. And so why does water stress reduce corn yields? The answer here is a reduction in radiation use efficiency. And so this yield equation is just so valuable when we're trying to think about, why are certain management practices, be that irrigation or nitrogen fertilization or weed management, impacting yields. It's this yield equation that's so powerful. So you will not ever need to actually solve the yield equation. I'll never give you a bunch of numbers and plug them in to figure out what yield is, but I just wanted to give a quick example here for those who were curious, because you can indeed solve for the yield equation if you have the numbers. So in the future, you may be asked to calculate the harvest index of a crop in answering a question. And this is a very fundamental measurement of crop productivity, so it's important to note, and it's also incredibly simple to do. All right, it's basically a ratio. You divide total grain yield by total above ground crop biomass, and so grain yield is typically expressed on a tons per hectare basis. So your total above ground crop biomass is also expressed in tons per hectare, and you just divide one by the other. So total crop biomass includes grain yield as well as stover biomass. Harvest index really only accounts for above ground crop biomass. We typically don't include roots in our harvest index calculations. And I'm just giving some examples here that shows you how to calculate harvest index. Again, simple. If you're having trouble with it, just come to the drop-in sessions that I'm hosting every Friday.